Hi folks, welcome to the beginnings of rational functions. I'm going to start with a very simple rational function, and a rational function is simply a function that is a ratio of polynomials. We're going to start with the most simple rational function we will often call as the base function. These are also called reciprocal functions because we start with the function f of x equals 1 over x. And that is your very basic function. I'm going to turn that off. You've got a brief glimpse of what it looks like. But I want to start by talking about how we analyze functions. Reciprocal functions or rational functions are a great tool for learning how to analyze functions. So, of course, let's remind ourselves f of x is the function notation. And what we're saying is the function for the input x equals, in this case, a rule 1 over x. So we're going to start off when we analyze these functions looking at the denominator, because the denominator in these functions is going to tell us something about what the function cannot be, or should I say, what inputs the function cannot have. And unlike quadratic functions or polynomials or linear functions or exponential functions, there are limitations on the domain or the inputs that this function can have. There are exceptions to this, but in this case, there is definitely a domain that this can't have, and so this function is not continuous. A continuous function would continue across all of the domains possible. It would not get interrupted anywhere, and it also doesn't have any, this one, well, let me back up. So it would not be interrupted anywhere along the way. A continuous function would not have a break. But this one is going to have a break. And this break is going to be at an x value that cannot be used. Now, the x value that can't be used in this case is 0, because we can't divide by 0. So I'm going to start off by setting up a vertical line at x equals 0. And I'm going to doctor that vertical line by making it a dashed vertical line. Now, you can't really see it so well because the y-axis is there, but I can actually turn off the y-axis so it's visible. So there's the y-axis. The y-axis is, in fact, a zone where x equals 0. And since when x is 0, this function can't work because you're doing 1 divided by 0, we have what is called a vertical asymptote. Nowhere along here can the function exist. However, the function is going to try and get closer and closer to that as it goes. So the other thing we can analyze about this is to figure out, are there any limitations on the output of the function? Well, it turns out there are. There is one number that the function can never equal. There is no way this function can equal 0, because there is no x value that you would ever divide 1 by in order to get this function to equal 0. So I'm going to make a second asymptote. This is called an end behavior asymptote. In simpler textbooks, it will refer to this as a horizontal asymptote. It happens to be horizontal, but what it's really doing is it's defining the end behavior of this function. When I say end behavior, I mean as x goes out to infinity in the positive direction or out to infinity in the negative direction. I'm going to refer to that as out to negative infinity or out to positive infinity. So I will set up another line at y equals 0, and this is going to be additionally a line that it cannot be. I'll make that a dashed line. You can't see it, of course, because you've got an x-axis. I'm going to make that x-axis go away. Notice I just hit the wrench and I click on x-axis, and now no x-axis visible. Cool. All right, so how do we track the behavior of this function then? Well, an easy way to do this in pretty much all cases is to set up a table of values. So we'll set up a table of values. We'll call that just x, and that's going to be 1 over x. And I'm going to start off with, we'll start off with 1, and we'll also do -1. Okay, so 1 and -1. Well, that makes sense. 1 over 1 is 1, and there we have a point at 1, 1, and 1 over -1 is -1. So -1, -1. That works. All right. Then what happens if I go out to 2 or -2? Well, if I'm at 2 or -2, 2 gets me to 1/2. So I'm at 2, 1/2, or -2, -1/2. All right. Just I'll remind us, of course, that 0 is undefined for this function. And I'll scroll down just a little bit more. And let's put in 3. Okay, 3 is 1/3. -3 is -1/3. 4, -4. How about 10? 10 is 1/10. -10 is -1/10. And so on. As you can see, as x gets bigger in either direction, the function tries to get closer and closer and closer to the x-axis. But what about going closer to 0? Well, as we get closer to 0, let's try 1/2. Well, if we get closer to 0, what happens is the function starts to go up, because dividing by a fraction, this is 1 over 1/2, well, that equals 2, because you can fit 2 1/2s into 2. We'll try 1/3, 1/4, 1/5, 1/6, 1/10, 1/20th, and that's off the screen, but there it is. And as we get our fractions to be closer and closer to 0, our function tries to get closer and closer to the y-axis, or x equals 0. This will happen in the other direction as well, and I'll demonstrate with that with a couple of points. I'll move this up so you can see. -1 over 5, -1 over 10, -1 over 20, and so forth. Now, let's turn the function back on, and you'll see that it matches up perfectly with all of, oops, let's go back and actually turn it on, matches up perfectly with all of those points. And there you go. All right, well, why does it get closer and closer? Well, it gets closer and closer to the y-axis because as the denominator gets bigger and bigger in either a positive or a negative sense, as the denominator gets smaller and smaller in a positive or negative sense, the function shoots off towards infinity or negative infinity, because you've got a 1 over a smaller and smaller thing, until you get to 0, in which point you can't do that because there is no number of zeros that would equal 1. On the other hand, there are a billion 1/billionths that equal 1. So when I have 1 over a billionth, then my y value will be a billion. On the other hand, as the denominator, as x gets bigger, it makes the fraction try as hard as it can to equal 0, but it never will, because there's no denominator that could ever make 1 over x equal 0. I'm going to stop with this one right now, and I invite you to experiment with things like this, basic, simple, rational functions in the form y equals 1 over x, maybe 2 over x, 3 over x, -1 over x, and so forth.